Okay, so before we start, kind of new stuff, I want to talk about a homework question, just to uh, maybe kind of more difficult, but just want to go through an example, um, of how to do it. So, first of all, let's think about if you have A and B that are symmetric matrices, and let's say they're the same dimension. A question on one of the homework questions is their product symmetric? So, I mean, what you could do is go through the definition of being symmetric, which is what, by the way? What does it mean for a matrix to be symmetric? Remember that? So there's two ways you can say that is it has to be square, but what property of a square matrix makes it symmetric? Yes, it's equal to its transpose. So you take the transpose of the matrix, we'll get the same thing back. So another way of saying this is that if I look at the ijth element of A, what is this equal to? When thinking about transpose. Like what happens when you flip row and column? Yeah, so any element in the matrix is equal to its swapped position, HAI. So, however, in the product of two symmetric matrices, it may not necessarily be true. I mean, if you just look at the product definition, AIK BKJ, if it were symmetric, this would equal AJK BKI. Right, that's what you would want if the product was equal. However, so you might get kind of stuck here, like how do you go and prove that's true? What we can do is just find an example where it doesn't work. So I'm going to give an example where it doesn't work. Here are two symmetric matrices. Do you agree that these are symmetric? So, right, if I take the transpose of the first one, right, it's going to be the same thing back, and similarly, the second matrix transpose is the same. So let's say the product of this. So I get 3 plus 2 is 5. Get 1 plus 4 is 5. But here I get 6 plus 1 is 7. And 2 plus 2 is 4. Can someone say why this is not symmetric? I have not announced it in the midterm. It'll be on Blackboard when it's announced. Why is this not symmetric? What's the transpose? Yeah, 5 and 7. So what would the transpose be? Yeah, 5, 7, 5, 4. Here's an example of two symmetric matrices whose product is not symmetric. So, so this one you had to come up with an example that doesn't work. So in general, when dealing with these questions, if no, you need to come up with a counterexample. That's enough to show that it's not generally true, obviously. However, if it is, in this case, it ends up, it will be symmetric. Now, can you if something is generally true, does an example prove it? Like, is it enough just to find two matrices where the sum is symmetric? No. And why is that? Well, I can find two matrices whose product is symmetric. Here's two matrices whose product is symmetric. This will have, we can even make them different. The product of, or let's make them even more different. Let's see what the product of this would be. So in the first one, I get 6, I get 2, I get 2, and 6, right? That's symmetric, but we just found an example before where the product of two matrices was not symmetric. So even though I came up with an example where the product is symmetric, that doesn't say that every single product is symmetric. So if you want to prove something is generally true, you have to come up with a general proof. So what do you think you would need to do when coming up with general proof of these things? So like, what's the definition of multiplication that we have that could be used generally? We would probably have to use this definition of multiplication. All right, so let's just do that. So here's the general proof that, well, let's look at the ijth element of here, and we're going to see if it's equal to the jith element. So this is a I k b k j, and this is b I k a k j. So we can put these sums into one thing because they're the same dimension, and that's what matrix addition is. So we have a I k b k j plus b I k a k j. Okay, so our goal is to try to show that this is equal, in fact, to this, but at the jith position. So we know that A and B are symmetric. So how do you think we can use that fact in our proof here? If we know that A and B are symmetric, what do you think we can do to manipulate these terms? So what's the only thing you can really do with a symmetric matrix to manipulate it? And when written out like this. What does symmetric mean again? Equal to transpose. So what does that mean by its coordinates? When you switch the coordinates, it doesn't change. So for example, if I were to switch the coordinates, I'll get the same thing back, right? So what is AIK switch to? KI, so let's do that. That's really the only thing we can do, right? All we know that it's symmetric. And then what does the B switch to? It switches to JK. And let's do that for every single term. Everyone see what we're doing here? Okay. So now we have this expression here but it's not in a form where you can do matrix, where it's not a matrix multiplication, right? So what do you think you can do to kind of put into a matrix multiplication form? So what do I mean by matrix multiplication form? Like, it's where the K's are like next to each other, right? So how do you make the K's next to each other? It's the trick that we did last time. Yeah, just switch them. It's just normal multiplication here. So we have B, J, K, and A, K, I, right? This is just normal number multiplication. So that's why we can do this. And now, what is this? What are these things here? What matrix has these coordinates? Yeah, yeah. And what coordinates are they? Are they IJ? Are they something else? JI. And then what coordinates are these? Also JI. So this whole thing is BA plus AB. Oh, and look, that's what we started with. We started with AB plus BA. So this is a general proof to show that the sum of AB plus BA is symmetric if both A and B are symmetric. That's pretty weird, right? But we showed that AB doesn't need to be symmetric. But when you add it to its, so when you flip the product, it becomes symmetric. So in number 10, I'll just kind of like give you hints, is that A plus B, A squared, and this one, these are symmetric. And then you can find counterexamples for the rest. And now I forget the rest. AB minus BA is not necessarily symmetric. And I think there was a third example that wasn't symmetric. Oh, ABA. These are not necessarily symmetric. Yeah, so I just did this one for you and this one for you. So you need to come up with counterexamples for the other ones and prove these. So prove, and then these are come up with counters. Okay, it's probably one of the harder ones of that homework, but I wanted to give you an example where we're actually using this matrix multiplication definition to prove something. Okay, so any questions on that, or questions on any other, if you started the homework? It's still got a while for it, but start early because there's a lot of questions. Proofs on the midterm, if they're short enough, yeah, but if they're long, like this is kind of long, so you may not see that on the midterm, but these ones are easier. So those would be valid kind of proof questions. I don't care about like being very specific with your proofs. I mean, or very rigorous. I mean, like this is fine. Yeah, you need sums if you're talking about arbitrary dimension, right? We couldn't do this without a sum, because then it would just be right. We kind of need that. So, I mean, it depends on the problem, of course. All right. So, oh yeah, so to finish up 1.4, we're going to talk about two things today. We can give a proof for, and this, of course, I would not ask you to do this in the midterm, but for the formula of an inverse of a 2x2 matrix. This is kind of what we ended with last time. So can someone tell me what inverse means? If a function is one-to-one, it has an inverse, yeah. But like, what does that mean in matrix world? It also means the same thing in function world, but how do you describe that in matrix? Remember, if you forget it, the definition, recall what the inverse of a number is, the multiplicative inverse. That's identity you wrote there, but identity plays a role in the inverse. So what is about the, so exactly, yeah. So just with numbers, right? The inverse of a number is the number you multiply to get, oh, sorry, not the 0 matrix, but the 1 matrix, right? Matrix that you add to get the 0 matrix, so that would be the additive inverse. So for multiplicative inverse, it's the matrix that you multiply to get the identity matrix, which is our 1. And that's the 1, 0, 0, 1 matrix for 2x2. Does that make sense? That's what inverse means. So it's kind of like, quote, division. We're going to see like why we kind of don't like the word division. So is that okay about definition of an inverse? Yeah. Okay, so what would that mean for a 2x2? So let's give our a random 2x2 matrix, A, B, C, D. And let's suppose it has inverse, and we don't know what the numbers are. But this is what it would mean to have an inverse. Is that it's a matrix that you multiply to get 1, 0, 0, 1. So let's actually just solve for the x, y, z, w. So these are now unknowns. You know, so now we're doing algebra, and we're actually solving for a matrix now. So it's kind of like, you can think of this as like A times big X is equal to I. Now we're solving for the matrix X. All right, so can someone read for me the matrix product? So what goes in the first position? AX plus BZ, good. How about in the 1, 2 position? AY plus BW. In the 2, 1 position? BW, yep. CX plus DZ. And how about in the 2, 2 position? CY plus DW. So this is equal to 1, 0, 0, 1. All right, so if two matrices are the same, what does that mean? There are 4 things that need to be true here, right? what must be true about AX plus BZ? Has to be equal to 1. Right? If you're claiming that these two matrices are the same, it has to be 1. AY plus BW, 0. CX plus DZ, 0. And then CY plus DW is 1. All right, so now we have a linear system of 4 equations. How many variables do we have? 4. So it's going to be a 4 by 4 system. Can someone read me the first row of the matrix? Keep in mind how many variables there are. And let's go X, Y, Z, W. So W is the last variable. So what's the first row of the matrix? So X, Y, Z, W are the unknowns. And A, B, C, D are the, there's AX's, there's 0 Y's, there's BZ's, there's 0 W's, and it's equal to 1. If I order the variables like that. So everyone see that? All right, so how about let's do the second. Someone give me the second row. Oh, you did Z last. That kind of makes sense, right? Because Z is the last letter. Yeah, so there's 0 X's, there's AY's, there's 0 B's, and or Z's, and there's BW's, and it's equal to 0. All right, let's keep going. The third row. C, 0, C, 0, 0, and then the last row. Zero. Sorry, this is a D, right? DZ. 0. Oh, that's a C. C, 0, D, and 1. That's okay. All right, so let's solve this now. So we're doing Gaussian elimination. So what can we do? Now there are letters here. There's not many numbers. But what was that general formula to eliminate an entry? So, I mean, what entry are we trying to eliminate? Let's try to eliminate that entry. So yeah, I remember the row op when it's not like a 1. Good, yeah, it's negative C over A. So you're changing row 3 and you're adding negative C over A, row 1. And again, why does that make sense? The A in the denominator means you're gonna cancel out the A in the entry there. And having a C on top means that you'll have a C entry. And why is it minus? Because you're getting rid of, you want to make this 0. Okay, so let's do that. A, 0, B, 0. I'm going to give myself more room. A, 0, B, 0, 1, 0, A, 0, B, 0. Okay, now let's see what happens to row 3. So you have a 0, 0. And now can someone give me the next coordinate? Next entry? So D minus, not C over A. What happens to that B? How does that B play a role? minus CB over A. Yeah. With the row 1 entry is B, right? And then you're multiplying a negative C over A, that's here. And you're doing D, right, minus that expression. So anyone have any questions about that? Does that make sense? Okay. Next entry is 0. And then what's the next entry? The last, in the column at the end. A little harder to conceptualize when there's no numbers. Yeah, this one is just negative C over A. All right, and then we have 0, C, 0, D, 1. All right, so now that we know how to do row 3, then the next operation might feel easier. All right, so now we want to get rid of this entry. So what is the operation? We're going to do row 4, and then row 4 plus 1. Also negative C over A. And which one are we using? We're using row 2. All right, let's do it. A, 0, B, 0, 1, 0, A, 0, B, 0, 0, 0. By the way, what happens if I just got it. What happens if you put this into one fraction, like common denominator? What do you get? Right, and I'm going to write it as AD minus BC for reasons later. And then let's read the last line out. 0, 0, 0, and then what's this position here? Same thing, yeah. So I might as well just jump to the combined fraction. And then what's this entry? The end. So this one's actually not negative C over A because our row 2 doesn't have a 1. So 1. All right. So let's solve it. All right, what's W? So this last row says that W times AD minus BC over A is equal to 1. So that means that W is equal to A over AD minus BC. You can see that? Is that good? Oh, why is there A in the denominator if you multiply a row by A? Oh, what I'm doing is just combining the fractions. I'm not multiplying the whole row by A. I want to avoid doing that because, W is just the 4th variable. Okay, so that's W. All right, and then what's Z? So Z times AD minus BC over A, that's equal to negative C over A. So what is Z equal to? Is equal to negative C over AD minus BC. right? Everyone see that one? Okay, so let's do y. The second line, second row reads ay plus bw is equal to 0. We solve for w, so it's ay plus b times a over ad minus bc is equal to 0. So we have ay is equal to negative ba over ad minus bc. So this means that y is equal to negative b over ad minus bc. Is that okay, the algebra? All right, and then let's read the last line. It's ax plus bz is equal to 1. So we don't know what x is, so it's ax plus b, but we do know what z is. It's negative c over ad minus bc, and this is equal to 1. So let's solve for x. We get ax equals 1 plus bc over ad minus bc. What happens if you combine the fractions? You get ax equals ad minus bc plus bc over ad minus bc. Let's cancel, and you get ax is equal to ad over ad minus bc. So x is equal to d over ad minus bc. Questions on that computation? All good? Okay, so we did it. We have all the entries we need for the inverse. So we can write it over here. So x is d over ad minus bc. How do we say y was? Y was the second one. Is negative b over ad minus bc. Z was negative c over ad minus bc. And our w was a over ad minus bc. All right, that's actually kind of nice, right? All of the entries have a common factor. What's the common factor? Right, 1 over ad minus bc. So d, negative b, negative c, a. That's a pretty nice formula, right? Remember, so this is the inverse of a, b, c, d. So it's just kind of like a rearrangement of the elements. Some get negated, and then times this factor of 1 over ad minus bc. So let's, oh, so by the way, I'll let you kind of try to figure out yourself, but there's a couple of things that we should have assumed, we assumed. A could not equal 0. Do you see why? What step forced us to say that A was not equal to 0? Yeah, we have a denominator. What would you do if A was equal to 0 in your first step, in our first step here? Then you would row swap and continue. Yeah. So you'll find out you get the same formula. but you would have like negative BC instead. So you should do that to kind of verify. All right, so when thinking about if a matrix has an inverse or not, can you identify when a matrix does not have an inverse? You can just look at the formula for the inverse. Zoom out, sure. Look at the formula for the inverse that we just came up with. How could you tell if a matrix does not have, a 2 by 2 at least, does not have an inverse? So in other words, what I'm asking is, what determines if a matrix has an inverse? How about a question, what is a weird part of this formula that sometimes wouldn't work? Really stare at that formula. What's a possible problem with that formula? Should be shouting at you. Yeah, that denominator is 0, right? What happens if this is equal to 0? It means it doesn't have an inverse. So last time we did give an example with a matrix with no inverse, which was this kind of thing that shines a light on the x-axis. So based on this formula, why does this not have an inverse? What's the AD minus BC? What's the A here? One. What's the D? And everything else is 0, right? So it doesn't have an inverse. So we showed it explicitly why it doesn't have an inverse. But with this neat formula, we can see why it doesn't have an inverse. So something we'll talk about in section 2.1, this AD minus BC determines if a 2 by 2 has an inverse. So we're going to call this if it determines it, we're going to call it a determinant. The determinant of a 2 by 2. So we'll talk more about determinant in 2.1, but we can do it now with the tools that we have. So for right now, all the determinant really tells us is that if it's 0, it has no inverse, and if it's not 0, it has an inverse. All right, so any questions on the formula for the 2 by 2? So one just kind of visual thing, all you really do is flip-flop the diagonal elements and then negate the other elements. And then you divide by this determinant that we just talked about. All right, so are we okay with that? We're gonna do something, we're just gonna do an example or two. Okay. And go on to the next page. Let's do 1, 3, 2, 1 inverse. Okay, so our formula says that it is, let's make something more interesting. 3. or let's say 4. Formula says that we flip the diagonal elements. So it's going to be 4, 1, and we negate the other ones. So -3, -2. And then we're going to multiply by 1 over this determinant. So it's going to be 4 times 1 minus 3 times 2. So this is 8 minus 6 here. So this is 1/2 times 4, -3, -2. Okay. So I'm going to see how we're applying the formula there. Okay. Let's check it. How can we check if this is truly the inverse? Maybe we made a miscalculation, or we forgot the formula and messed up some formula. How can we check if we did it right? Yeah, you multiply. What should it equal? Yeah, it should equal I. Okay, so let's do it. We have 1 times 2 plus 3 times -1. Did we make a mistake already? Negative. Wait, what? What happened? Oh, I'm sorry. I messed up everything. I read 4 times 1 is 8. 4 minus 6. It's -2. Thank you. -2, 3/2, 1, -1/2. This is why we multiply and check our work. So -2, 3/2, 1, -1/2. All right, is it okay now? All right, now let's do it. So this is -2 times plus 3, so that's 1. This is 3/2 minus 3/2. Cool, that's 0. This one is -4 plus 4 is 0. And then this is 2 times 3/2 minus 4/2. Okay, so that's 1, 0, 0, and this is 1. So good. All right. Questions? So very helpful. Check your work. Okay, let's do another one. Oh, can you go over the last part? Okay, so I'm multiplying. So this was the original A, and this was the inverse that we calculated. So this is A inverse here, and this is A. You see that? So these two matrices were multiplying to get this matrix. So this is A inverse.
Can you do like one example? Like, let's say, would you multiply the 1 by on the other side?
Oh, like how does this multiplication get this?
Yeah, yeah.
All right, so the first position, the 1, 1 position, is 1 times -2 plus 3 times 1, right? So that is -2 plus 3, which is equal to 1. So that's how we got a 1 here.
Yeah, I just forgot about it. Thank you.
Oh, it's okay. Yeah, so the formula was, right, for this case, the product 1, 1 would equal a 1, 1, a inverse 1, 1 plus a 1, 2, a inverse 2, 1. So it's a similar thing for every entry. Okay, so we'll do more examples and then we can get the hang of it. So let's do this one. What would the inverse be? Can someone tell me what it is or isn't? All right. 1, -1, -1, 1. Then I have this other thing here, right? What would that be? Yeah. Yeah, so this is has no inverse. So that doesn't work. All right. Let's do 1, 2, 3, 4. What would that one be? So I think it's good to do the determinant part first. Let's do 1 over. So what is it divided by? Remember, it was AD minus BC. Yes, this is 4 minus 6. So automatically, does this thing have an inverse or not? Yes, so that means we're good to go. So now let's do the formula. So it's 4, 1, -2, -3, and then we're done. So this is -1/2, 4, -2, -3, 1. Okay. Okay, let's do 1, 2, 3, 6. All right, what's the 1 over part? Uh-oh, 6 minus 6. Does this thing have an inverse? No. Okay. All right, let's do this one. We have a column and then a multiple times the column. So we see that AB and then there's CA, CB, so that's a multiple of the column. So what is the 1 over part? ABC minus ABC. Uh-oh. Yes, so when we do 2.1, we'll talk about what the determinant is for a 3 by 3. Now, if you imagine, it might be a bit harder to do it for a 3 by 3 because it would be a lot more variables, a lot more equations. It'd be 9, right? It would be 9. There's 9 positions in the 3 by 3, right? So it's going to be a 9 by 9 system. So we're going to do a little magic to make it so we don't actually have to solve a 9 by 9 system. But we will come up with like a formula, but we're going to talk about it differently. So it's not a formula they have to memorize. All right, so that's no inverse. That's nice. So what is the claim here? If the columns are scalar multiples of each other, and this is in a 2 by 2, it's going to be the same for a 3 by 3, then no inverse exists. That's pretty nice. So you can kind of just look at it. For example, this one. All right, 3, 6 is a multiple of 1, 2. All right, it's times 3. Now you get 3, 6. Okay, how about this? Also, ABC minus ABC millimeters. So, and if the rows are scalar multiples of each other, then no inverse exists. All right, so just giving it a definition. If a matrix has an inverse, it is called non-singular. If the matrix does not have an inverse, it is called singular. The meaning of that word will kind of make more sense later in the course, like towards the end. It's kind of counter, right? If it does not have an inverse, it's singular, but if it has inverse, it's non-singular. But for reasons later, we'll talk about why, that those words mean what they mean. So, so what is the determinant? The determinant. So if the determinant of a matrix is 0, it's not really a definition, it's called the matrix is singular. All right, so any questions on those definitions? So we'll talk about what determinant means for 3 by 3, 4 by 4, 10 million times 10 million. And there'll be a general formula for that. We could do 10 million. That might be hard to do though. All right. Oh yeah, one more example I wanted to do. The matrix. That's what it is referencing to. Now, of course, it's all n by n. Sorry? Oh, it is called singular. Yeah, just for bits. I'll let you do this one yourself, but these are singular. If you have a row or column full of zeros, it's automatically singular, has no inverse. So we can just do it to see that, but that's going to be a very handy tool when we do 2.1. Okay, so let's talk about some graphs for a bit. Okay, it's a cool subject in math. So, so one of the first kind of books and papers on graphs was called had a name called Dots and Lines. I think it's funny. So it's just a collection of dots and lines, and how to connect dots and lines on a page. So and we can actually use matrix algebra to talk about properties of graphs. So graphs, you might think with the computer networks, Instagram or Facebook, people you follow. There's a graph going on there. Well, once we kind of explain what a graph is, you'll see why that's true. So let's just say what a graph is. So a graph is defined by two sets, a vertex set and an edge set. So what is the vertex set? It's a finite, not finite, it's countable set of points on a plane. So these are just dots on a plane. And so, just for example, like V1, V2, Vn. So so you can call them vertices. So we call the vertices maybe V1 through Vn. And there's n vertices, for example. Oh yeah, GPS. Finding the shortest distance between, that's a complicated problem. Find the shortest path between two things. And what is the edge set? So it's pairs of vertices. So let's say Vi and Vj is in the edge set if there is a line or edge between Vi and Vj. That's how we're going to find an edge. So notice that edges need to be in pairs. You can't have an edge with just one vertex. It has a beginning and an end. But there's nothing that says that there need to be any edges at all. So let's just give kind of some examples of graphs. Here's a graph. What's the vertex set? How many vertices are there? 3. So let's label them V1, V2, and V3. What's the edge set? Yeah, there's nothing. So there's nothing there, it's empty. Okay, let's be more interesting. Okay. What's the vertex set here? There's 4 of them. So let's say V1, V2, V3, and V4. Now let's label them. And what's the edge set? So remember, the edges look like look like a coordinate. There's two edges. So what are the two edges? V1, V2, and V2, V3. So notice, by the way, that V1, V2 can also be expressed as V2, V1, right? They're not a different edge, right? It's just one line there, but V2, V1, it means the same thing as V1, V2, but we don't label as a different edge. So you can flip the order of the vertices, and it's not like a new edge. Sometimes there are other graphs where you do think of them as different edges. It's called a directed graph. Has a different edge set. Where Vi, Vj is not equal to Vj and Vi. So you could have something like this, where you do care about the direction. So what I like to think of this as, if you don't care about the direction, it's kind of like a Facebook friend, where you're both friends, right? So doesn't matter if you're friends with them and they're friends with you, but you can't just be a friend with someone and they're not friends with you. But a directed graph is like maybe like Instagram, where you can follow someone, but they don't need to follow you back. So the order does matter, and who is the follower and who's followed. So Instagram is more like a directed graph. We won't talk about directed graphs, but that's there. Another type of graph is the one that we'll talk about more. It's called a simple graph. A simple graph has no multiple edges and no loops. It's also kind of more like we're used to, like Instagram, whatever. You can't follow yourself, right? And you can't follow someone more than one time. So we're going to talk about things where they don't have loops, and there's going to be no multiple edges between them. But you can talk about stuff where graphs are non-simple, and there's a lot of cool stuff you can talk about with that. All right, questions on what a loop is and a multiple edge? So Vi, Vj only appears once. That's a simple, and there's no Vi, Vi. So there's no Vi, Vi, which is a loop, and Vi, Vj can only appear once. So that's what we're going to call a simple graph. All right, so one other thing is isomorphic graphs. If G1 and G2 have the same vertex and edge set, they are called isomorphic. This means that, so in other words, they're the same under relabeling and rearrangement. Arrangement. So it turns out like this is actually an open problem in math. Is there an algorithm to show whether two graphs are isomorphic? I mean, of course, you can have very complicated looking graphs, but there's no known algorithm to determine this. So here's an example of two isomorphic graphs. So why, can you say why they're isomorphic? Like why are they the same graph? So really when I say isomorphic, I mean they're the same. Vertex, so that's the V set. This is V set here, if the vertex set are the same. Yeah, so, and so let's say if I say this is A, B, C, D, and let's call this V1, V2, V3, V4, right? The vertex set is A, B, C, D here. And the edge set is, can someone tell me the edge set on the left? Yeah, AB is an edge. BC is an edge. BD and CD. Yeah, so they're the same under relabeling. So vertex relabeling, which implies edge relabeling, sorry. Relabeling and rearrangement. It's arrangement. So even though I call these A, B, C, D, and I call these V1, V2, V3, V4, they're the same because they're essentially the same graph because I can just call A V1. I can call B V3. In this case, V3. And I get the same edge set. So the idea is that you can just call A V1, you can call B V3, you can call C V2, and you can call D V4. So what is the relabeling? It's calling A, B, C, D the same as V1, V2, V4. And the rearrangement is that the graph can look different, right? But it's still the same thing, still the same graph. They're essentially the same. Questions on that? So essentially this means that like you can rearrange it, you can stretch and shrink the lines as long as the vertex and the edge set are the same, they're essentially the same. So the isomorphic means just the same. Iso means same. Questions on that? All right, so where does matrix algebra come in? Yeah, the shape doesn't matter. So here's another thing that will also be the same. That's also the same. They don't have to be straight lines. Yeah, at the end of chapter 1.4. Oh, no, yeah, they don't have to have for edge. Here's something that's not the same. So they won't have the same edge set, right? What's special about this edge set? There's something in this edge set that's not true in this edge set, right? Because B, or this one, has 3 edges coming from it. But the square, for example, all the vertices have 2 edges that come from it. Does that make sense? Like why they're not the same? Like there's no correspondence between the vertices that give the same edges. All right, so let's talk about something called, so this is where the matrix comes in, the adjacency matrix. And we'll probably do more of this next time. But let's just define what the adjacency matrix is. So let G be a graph. And we're going to call the adjacency matrix of the graph, and we're going to define what the coordinates are. So, sorry, I should say a little bit more. Let G be a graph and let the vertex set, let there be n vertices. There's no infinite vertex graph here. There's n vertices. So the adjacency matrix of G is going to be an n by n matrix. And the elements in the matrix are going to look like this. And it's very, very easy. So it's going to be a 1 if this is the case. If Vi, Vj is in the edge set. So you're going to give some labeling to your vertex set. It does not matter what labeling you use because of the isomorphism thing, right? If you use one labeling and your friend uses another labeling, they're still going to be the same graph. So if an edge appears between 2 vertices, we're going to put a 1 in that position. And you're going to put a 0 if there is no edge between them. That's it. Does that make sense, the definition? So let's just do an example. Let's do the one that we were looking at before. Called V1, V2, V3, and V4. So what dimension matrix is this point? The adjacency matrix is going to be? We're almost done. What's the dimension? Yeah, it's 4 by 4. So now let's look at the edges. Is V1, V2 in the edge set? Yes, so that means that 1, 2 is in the edge set. It is 1 is in the position 1, 2. Is V1, V3 in the edge set? No. Is V1, V4 in the edge set? No. Is V1, V1 in the edge set? No. All right, so the second row, V2 is connected to V1, so you put a 1. V2 is not connected to itself. V2, V3 is connected, and V2, V4 is connected. V3 is not connected to V1. V3 is connected to V2. It is not connected to itself. It's connected to V4. V4 is connected to not V1, but is to V2 and V3 and not itself. So does that make sense how we constructed that? We'll do more of this next time. But big question. What type of matrix is this? What nice quality does this matrix have? Based on something we talked about in the beginning of class, it's symmetric. Yeah. Why is it symmetric? Based on the definition. So symmetric means that if you flip the row and column, it's the same. And why, just based on the definition, would you assume that's true? So if VI and VJ are in the edge set, does that imply that VJ, VI is in the edge set? Well, of course it does, right? If VI is connected to VJ, then VJ is connected to VI. So this is not directed. Okay, so that's it. Next time we'll talk about like, what do powers of the adjacency matrix mean? So that's kind of interesting. So we'll do more of this next time. Yeah, so I should say that this is directed. I mean, you probably could talk about, sorry, not directed. Oops. Yeah, undirected, yeah. If you define it for directed, it wouldn't be symmetric anymore. But I'm not sure how you can use that, if that is used as much. But the nice thing about not direct is that you get a symmetric matrix, which is very nice. All right, so I'll see you Monday. So still just gonna finish up 1.4 on Monday. Oh, do we have off Monday? Holiday, okay, so I guess Wednesday. I can start recording.